Hello everyone and welcome to the aTech channel. Today we're going to talk about a revolution that could solve the energy question. Wind and solar power are becoming increasingly popular, and there's enough energy from the sun and wind to power the world. Unfortunately, they are intermittent. We need vast amounts of energy storage and can't simply install wind and solar farms wherever we like. Yet there is an almost unlimited, clean, reliable, and sustainable source of renewable energy, available 24 hours a day, every day, and everywhere in the world. It could provide all the energy we need for years to come. We're talking about geothermal energy. So, why aren't we building geothermal power plants everywhere? Geothermal energy is one of the most promising sources of renewable energy, and at the same time, one of the least used. It works by capturing heat from the Earth's core, then transporting it to the surface. We can use it to heat our homes or convert it into electricity. In the latter case, geothermal power plants operate in a similar way to thermal power plants. They use hot pressurized steam to activate a steam turbine that drives the generator. However, instead of burning fossil fuels to produce hot steam, heat from the Earth's core is used. So how much geothermal energy is available? Some of this heat comes from the remains of the Earth's original formation. But how much of it comes from nuclear fission reactions triggered by the decaying radioactive elements present in the Earth's core? With all this internal energy, the Earth's solid core reaches a scorching temperature of up to 10,800 degrees Fahrenheit, which is about 6,000 degrees Celsius. That's almost as hot as the surface of the sun. This heat is transferred to the outer layers, creating a geothermal temperature gradient extending right down to the Earth's crust. The use of geothermal deposits is therefore an inexhaustible source, which we have been using for thousands of years as a source of heating, and since 1949 to generate electricity. Compared with most other energy sources, geothermal power plants have a very small footprint, especially when it comes to land use. In fact, geothermal is number 2 in terms of footprint, second only to nuclear power at 0.95 acres. What's more, they can draw on the knowledge and equipment of the oil industry. This makes it an attractive solution for major oil companies, enabling them to recycle millions of dollars in equipment and infrastructure, and all the while ensuring a stable source of income to replace their previous oil-related activities. So why aren't we building those power plants everywhere? The installed capacity of geothermal power plants worldwide reached only 15.6 gigawatts in 2021. Or approximately 0.6% of current electricity consumption. To do this, we need to understand how geothermal energy production works. Geothermal energy has 2 main applications: as a direct source of heat or to transform this heat into electricity. When we talk about direct use, we mean the direct transfer of heat from the earth to residential, commercial, or industrial buildings via district heating. All these power plants use steam turbines to power electricity generators. The rest of the system comes in many variations, the most common of which are dry steam, flash, and binary cycle geothermal power plants. The first technology was originally invented by François de Larderel, but put into practice by Prince Piero Ginori Conti in Italy. This system feeds a turbine with hot steam extracted from porous, high-temperature underground reservoirs. The steam is then cooled, condensed, and pumped back into the reservoir as liquid water. These models are not very common, but some of the geyser units in California operate on this type of generator. Unlike dry steam geothermal power plants, flash thermal power plants extract liquid at high pressure and temperature and send it to a reservoir, where it then evaporates. This produces high pressure steam, which is then fed into the turbine. Finally, we have binary cycle power plants, which generally use liquid water. The aim is to extract heat from the permeable reservoir and transfer this heat via a heat exchanger to an active fluid. Binary power plants are great because they can operate at much lower temperatures, and therefore at much shallower depths than dry steam and flash power plants. All these technologies are mature and have already been deployed on a commercial scale around the world, but they have several drawbacks. The biggest problem preventing global geothermal deployment is finding suitable sites for their construction. The basic requirements include heat, steam, and liquid water, and most importantly, fractured permeable rock. We can always find geothermal heat if we drill deep enough, but rock permeability is a challenge. There are only a few accessible places on Earth where traditional geothermal energy is feasible. It would seem, therefore, that the vastness of this energy beneath our feet is inaccessible. In the United States, for example, the country's east coast is virtually devoid of geothermal potential with current technologies. The second major challenge is cost. The process of exploring by drilling into the ground, building a power plant, and generating electricity is very expensive. This makes it more expensive than large-scale onshore wind and solar power. Finally, there is a proven connection between water pumping through injection wells at geothermal sites and large-scale seismic activity in the region. Although these tremors are not violent, it is a parameter that generates resistance from local communities. So we can't build them just anywhere, and they're expensive to build. They're not an attractive option for investors, and they scare off local populations. Does this mean the end for geothermal energy? Of course not. There are two promising new technologies that could potentially change the game for geothermal energy, one of which we've already seen go to commercial scale. Both aim to solve geothermal energy's biggest problem, the need for fractured permeable rock. The first technology is called Enhanced Geothermal Systems, or EGS. EGS is a geothermal power plant that artificially creates the necessary porosity inside the earth. This is to allow water to circulate between an injection well and a production well. This is achieved by pumping cold water into hot, solid rock, causing it to crack due to thermal contraction and water vapor pressure. EGS pumps only water, so there's no risk of groundwater contamination, as there is with the natural gas and oil. And this also happens at a much lower pressure, so the risks to the site's geological stability are much lower. Yet the slight risk of geological instability is the price we pay for access to geothermal energy everywhere, which is considerable. There are already several commercial EGS plants. So at this point, if you're incredulous about the prospects offered by EGS, here's some good news. There's another alternative that looks even more interesting. It's being developed by an Alberta-based technology company called Ever. They've designed the perfect geothermal solution, the Advanced Geothermal System, or AGS, primarily around their Everloop product. This essentially works by connecting an injection well to the production well through a sealed pipe, completely eliminating the need for fractured rock. There are absolutely no greenhouse gas emissions. There is no risk of groundwater pollution, and we can even use liquids other than water to extract heat more efficiently, which is not an option for other geothermal systems. The first Everloop was built in Canada and has been in operation since 2019. However, this promising solution has yet to reach commercial scale. If it does, it could finally open the door to an unlimited source of energy. It would then be a real candidate to replace fossil fuels on a global scale. If you enjoyed our topic of the day, please feel free to like this video. For more videos of this kind, subscribe to our channel. And don't forget to leave us suggestions for future topics. Activate the notification bell to be among the first to see our next video. See you soon on aTech.